All right, let's get started. So we're going to continue our discussion of thermodynamics. We'll be wrapping that up this week. We spent a lot of time last week talking about how to calculate enthalpy for different reactions. We have a few different methods to do it. All right, so we're going to practice those real quick so we can use these reactions as examples to build off of here today. So everybody take a second and copy down this precipitation reaction here. And then we're going to turn it to our standards page, our constants page, and you're going to calculate the enthalpy change of this reaction here. So copy down our chemical equation. What are we going to have to do with it before we can use it? Got to balance it like we always do. All right, and then this is a precipitation reaction. So when we go to look up these compounds on our constants page, we won't be able to find lead nitrate aqueous anywhere. Instead, what are we going to look up for these precipitation reactions? Right, we don't look up the full equation here. We got to simplify this equation. What are we going to create here? The net ionic, absolutely. So step one, we got to balance. Step two, we need to transform this into its net ionic equation. All right, so I have the net ionic here. So I'm going to bring up our constants page. All right, fortunately, everything that we need is located in this box here, or on this one page. So everybody take a second and hunt down our values that we need for this problem. So my reactants are this lead ion and the chloride ion. And my product is that solid lead 2 chloride. Okay, so I'm just going to copy this back on our other page here. When we do our delta H for our reaction, it's the sum of the delta H of the products minus the sum of the delta H of our reactants multiplied by their stoichiometric coefficient. So I'm going to take that negative 359.4 and I'm going to subtract the sum of my reactants. I'm going to need to put that in parentheses so I don't mess up my order of operations. I need this minus sign to be distributed to both of those reactant values. So that's the 0.92 plus 2 times the negative 167.1. All right, and where did that 2 come from? Our coefficient in our balanced chemical equation. We got to multiply that negative 167 by that coefficient in our balanced chemical equation. So punch that into our calculator. Get negative 26.12 is what my calculator spits out. Or if I'm being good about my sig figs, negative 26.1 kilojoules per mole. So what can we say about this reaction? Is it endothermic or exothermic? Exothermic. And how are we telling? What are we looking at? Just the sign out front of that value, right? A negative value lets me know that this reaction is exothermic, meaning the reaction will release heat. If it was a positive value, that would mean that our reaction was endothermic, or a reaction that absorbed heat. All right, so given this balanced chemical equation here, we can use our constants page to look up the values. For these particular precipitation reactions, we only care about the ions that are involved in our reaction. We don't care about our spectator ions. So what we're going to first do is get our net ionic equation, and that's what we'll look up on our constants page to find the delta H for our reaction. All right, so we'll use this reaction as an example to build off of, but let's practice one more way of calculating these, and this was introduced last class. These are using these bond dissociation energies. So not every compound in the world is listed on our constants page. So instead, we have this way of predicting what these enthalpies will be, really estimating what these enthalpy changes will be in a reaction by looking at the amount of energy required to break a bond, and that's equal to the amount of energy that will be released when that new bond is formed. So what we're going to do is we're going to take this is now just a chemical reaction, but we're specifically looking at the Lewis structures here. And by looking at the Lewis structures, we'll be able to determine which bonds are being broken in this reaction, and which new bonds are being formed in this reaction. All right, I think it might look a little intimidating looking at these molecules here because they're big and ugly. They're much larger than the ones that we learned how to draw Lewis structures for. But really, this is a game that you can play without knowing any chemistry at all. Just a simple spot the difference game here. What do we see on the left-hand side that isn't on the right-hand side? That would be our bonds that are broken in this reaction. And what do we see on our product side that isn't there on our reactant side? That's what new bonds are going to be formed in our reaction. Right? So it's a simple spot the difference game. What differences do I notice from the left-hand side to the right-hand side? All right, so everybody take a second. There are two bonds. Oh man, I messed this up. Hold on. Trying to make this impossible for y'all. These should be chlorines. All right, my bad. So there are two bonds being broken in this reaction, and there are 3 new bonds that are formed in this reaction. All right, so everybody take a second. Copy down our problem here, drawing our Lewis structures, but then see if you can identify which bonds are being broken and which new bonds are being formed. All right, can anybody see one of the bonds that are being broken in this reaction? What's a bond that's on the left-hand side that's not on the right-hand side? So we have this chlorine-chlorine bond that's going to have to be broken. There's one other one on the left-hand side that isn't on the right-hand side. The carbon-carbon double bond here, right? We have a double bond on this side, and on this side we only have a single bond, all right? So we're going to have to break that double bond, and then we'll reform one carbon-carbon bond, our single bond. All right, we have to keep track of these separately. If we look carefully here at these values, a carbon-carbon single bond versus a carbon-carbon double bond, we can see that this is not, a double bond is not just simply two single bonds together, right? That value of 614 is less than what you would get if you multiplied this number by 2 here. All right, so a double bond is not simply two single bonds together, so we're going to have to keep track of these separately. What other new bonds do we have on our product side? Yeah, we have this carbon-chlorine bond. We have a second carbon-chlorine bond as well. All right, so all of our bonds that are broken here, we're going to list those. All right, so we'll do this separately here. We're going to calculate the delta H of our broken bonds. And we need a carbon-carbon double bond plus our chlorine-chlorine bond. All right, our carbon-carbon double bond, that's that 614 kilojoules per mole. That chlorine-chlorine bond, I looked that up on my table here. That's 242 kilojoules per mole. All right, so that means that the total amount of energy that I have to put in order to break these bonds is 856 kilojoules per mole. All right, and again, that's the amount of energy you have to input. That's the amount of energy that's absorbed by this reaction here. All right, so now we're going to do the same thing, but with the other side. We're going to calculate the amount of energy that's released when these new bonds are formed. We have a carbon-carbon bond, and then we have two carbon-chlorine bonds. So I'm going to add all of those up, finding them on my table here. Carbon-carbon single bond, that's 348 kilojoules per mole. And each of these carbon-chlorine bonds is 328. All right, so when we add all that up, that corresponds to 1,004. Again, our units are kilojoules per mole. And importantly, this is the amount of energy that will be released when those new bonds are formed. Right, so chemical reactions are all about this give and take. Yeah, you got to put energy in to break your old bonds, but then you get a bunch of energy that's released when those new bonds are formed. And so then to calculate the delta H of our overall reaction, we're going to have to take the amount of energy that was required to break those bonds and subtract the amount of energy that's released when those new bonds are formed. All right, so when I do my math here, I get negative 148 kilojoules per mole. That's my delta H for this reaction here. Again, I added up the amount of energy required to break that carbon-carbon double bond and that chlorine-chlorine bond. That was that 856 kilojoules per mole. And then I subtracted the amount of energy that would be released when 2 new carbon-chlorine bonds and 1 new carbon-carbon single bond was formed. That's how I got that negative 148. All right, so just to make this a little easier to work with here, we drew out our reaction with these Lewis structures. I'm just going to sort of simplify things by writing our molecular formulas here. So this molecule here had 3 carbons and 6 hydrogens, plus that Cl2. That gave us our product here, which again had 3 carbons, 6 hydrogens, and 2 chlorines. And this reaction had a delta H of negative 148 kilojoules per mole. All right, so here's just kind of summarizing what we established through our calculations here. All right, and again, why would we bother doing it this way with our bond dissociation energies? Well, because for these larger molecules, we can't find every single molecule on that constants page. Right? So instead, by taking a look at what bonds are being broken, how much energy we have to put in, and what new bonds are being formed, how much energy is being released, we can get a good approximation of the change in enthalpy of this chemical reaction. All right, so now let's take what we learned. We'll first start with this one here. All right, as our example reaction. And now we're going to learn how to do some stoichiometry with our enthalpies. All right, stoichiometry, not going anywhere, right? We've talked about it in pretty much every chapter that since it was introduced, or at least every unit since it was introduced. And now we're going to do so here again in the context of our enthalpy of our reactions. All right, so we said that this was PbNO3 2. And we calculated the delta H of this reaction to be negative 26.1. kilojoules per mole. All right, so our units of our enthalpy here, negative 26.1 kilojoules per mole. All right, so this is what we established based on our constants page. Again, that enthalpy is in kilojoules per mole. All right, but importantly, what is that mole that we're talking about, right? We've been calculating our enthalpy for these reactions in kilojoules per mole, but mole what? All right, and this is where things are a little different here because now we're talking about this reaction itself. So I'm not talking about just a mole of, for example, sodium chloride. I'm talking about a mole of reaction. When you write your balanced chemical equation, you're establishing what your reaction is, right? This is our reaction here. So every time 1 mole of of lead 2 nitrate combines with 2 moles of sodium chloride to give us our 1 mole of solid product and our 2 moles of sodium nitrate, we would say that that was 1 mole of reaction that was occurring. All right, so let's remind ourselves, a mole is just kind of analogous to a dozen here, right? So if I had 1 PbNO3, combining with 2 of the NaCl's, we would say that that was 1 reaction. All right, well, if I had 1 mole of PbNO3 combining with 2 moles of sodium chloride, I would say that 1 mole of reaction has occurred. And again, chemists love their moles, so we love talking in moles of things. We're never talking in individual atoms or individual molecules. They're just too dang tiny, right? When we're doing a reaction, there is approximately 2 moles of water in this container right here. So that's a much more convenient way of talking about the amount of water as opposed to the 2.5 times 10 to the 24 water molecules that are in this container. So same thing with reactions. When we're talking about how much reaction occurs, we say 1 mole reaction occurs. And what does it mean to be a mole of reaction? Well, we established that when we drew our balanced chemical equation up here. That's our mole of reaction. When 1 PbNO3 mole reacts with 2 moles of sodium chloride. All right, so just like we did before when we were talking about reactions, how much product is formed in this reaction? All right, we needed to build those stoichiometric ratios. We're going to do the same thing here, but using that mole of reaction. So in this example here, there is 1 mole of PbNO3 that is consumed per mole reaction. And PbNO3 is a reactant, so it's consumed. Likewise, my other reactant, there are 2 moles of sodium chloride that are consumed per 1 mole of reaction. Again, sodium chloride, also a reactant, so this is also consumed. All right, so take a second and build me the mole ratio that we would get for our product, our lead chloride, lead 2 chloride. How many moles of lead chloride are produced in a mole of reaction? All right, according to my balanced chemical equation, just 1. All right, so again, just like before, we can look at our balanced chemical equation and we can get a whole bunch of these stoichiometric ratios. All right, and these tell us how much reactant is consumed, or in the case of a product, how much product is produced per mole of reaction that occurs. All right, so let's say if 0.25 moles of NaCl are consumed, how many moles of reaction have occurred? I believe in y'all. Everybody take a second. See if you can't perform this calculation here, all right? It's a little bit different than what we've done before, but really not that different in terms of our strategy for solving this. We're going to set it up paying careful attention to our units, making sure that our units cancel out and that we're left with what we want, which is in this case moles of reaction. All right, so I'm going to look at my balanced chemical equation. I can create all these different stoichiometric ratios here. but specifically I want the one that relates how much NaCl is consumed for how many moles of reaction have occurred. So I'm going to use this middle one here. I'm going to start with my initial value of that 0.25 moles of NaCl. And then I'm going to have to use my conversion factor, but I'm going to use it in such a way that those moles of NaCl cancel out. So I'm going to divide by that conversion factor so that my moles of NaCl are on the bottom. Moles of reaction are on top. When I do my math here, I'll have my moles of NaCl canceled out, so I'll be left with units of moles reaction. And then punch it into my calculator here. 0.25 divided by 2. My calculator spits out 0.125. All right, and of course the last step is going to be sig figs. Remember these mole ratios, these stoichiometric ratios that we get from our balanced chemical equation are exact. So that's not going to limit me in my sig figs. I'm going to need to round this to 2 sig figs here, or 0.13 moles of reaction have occurred. All right, so a little different, but not too crazy here. When we've been calculating our enthalpies here, we've always listed our units in kilojoules per mole. But mole what? All right, when we're talking about calculating our enthalpy using this balanced chemical equation right here, what we've calculated is the enthalpy change per mole of reaction that occurs. Reaction just as written up here, right? So our reaction as written says that 1 mole of lead nitrate is going to combine with 2 moles of sodium chloride to produce 1 mole of our solid product and 2 moles of our aqueous product. That's our balanced chemical equation. So that's what we define as a mole of reaction, right? So if 1 mole of lead nitrate was consumed, we would release this 26.1 moles of, kilojoules of energy, because that's a mole reaction, right? So we can take that and we can create these stoichiometric ratios just like we did before. All right, so now let's roll it all together here. All right, I'm going to ask you something similar, but with a slight twist here. Let's say if, we'll keep the value the same, those 0.25 moles of NaCl are consumed. How much thermal energy is absorbed or released by the reaction? All right, and you're going to start this out the exact same way as you did before to convert to moles reaction, but now we're going to need to use our enthalpy that we calculated. All right, and again, what we got is a delta H equal to negative 26.1 kilojoules per mole. We need to take this and turn it into something that we can use in our math, something that's going to allow our units to cancel out. And what we're going to do is the same thing that we did with molar masses and with our molarities. We're going to take these 2 units of kilojoules per mole and we're going to split them up. We're going to put 1 on the top, the negative 26.1 kilojoules, and then we're going to keep the 1 mole of reaction on the bottom. And so this is how we take that enthalpy that we calculated, right? We learned 3 different methods of calculating these delta H values here. Once we get that delta H value, we can take it and we can split up those units to turn it into one of those conversion factors that we can use in our math. All right, so then what we would do is just set this up just like before, where we take our 0.25 moles of NaCl. We're going to first need to get into moles of reaction, because that's what my enthalpy is defined as. And so we're going to have to use that stoichiometric ratio that we get from our balanced chemical equation that tells us that 2 moles of NaCl are consumed for every 1 mole of reaction. All right, if we stopped here, we'd have how many moles of reaction are occurring. But now we're going to do one more step where we use that enthalpy information. All right, this allows us to convert from moles of reaction into kilojoules of energy. and so if we punch this in here, we're going to get negative 3.2625. What are my units here? Kilojoules. Because the moles have now canceled out. My mole of reaction has canceled out. So this is how many kilojoules of thermal energy are going to be either absorbed or released by this reaction. If I'm going to do my sig figs, I'm going to have to round this to negative 3.3 kilojoules. And is that thermal energy that is absorbed by the reaction or energy that's released by the reaction? Released. And how do we know it's released? The negative sign, absolutely, right? Exothermic reactions will release energy. All right, so if we only take 0.25 moles of sodium chloride to react it, we're not going to get all 26.1 kilojoules of energy. That's for 1 mole of reaction. But we can do our normal stoichiometry game and say, all right, if that 0.25 moles of sodium chloride are consumed, then I can figure out just how many kilojoules of thermal energy are either absorbed or released. And again, the absorbed or the released comes from the sign. Exothermic reactions release energy. Negative enthalpy releases energy. A positive enthalpy means that that energy is being absorbed by that reaction. All right? Cool. All right, so let's just do one more practice thing here with our other reaction that we studied, the one where we calculated our change in enthalpy using that bond dissociation energy chart. All right, so now I'll say if 4.5 grams of Cl2 is consumed, how much thermal energy is absorbed or released by this reaction? All right, and to be clear, I'm going to go ahead and copy and paste that balanced chemical equation with our change in enthalpy that we calculated here. All right, and since we're talking about grams of chlorine, what am I going to need to use in this calculation here? I got grams of chlorine, but then I need my balanced chemical equation, which is going to be in moles. How am I going to get from grams to moles? Molar mass, yeah, so our periodic table. So I'm going to go ahead and copy down that value over here just so we have it on that same page. If you use the one on that chart, that's fine. I don't know if they're exactly the same. Oh, they happen to be exactly the same, so that works out well. All right, but 35.4527 grams per mole for chlorine. right, so one of the tricks here is how we're going to take this molar mass here, but we got to convert it into something that we can use in our math. So we're going to split up those units. So this is going to be 35.4527 grams of my chlorine in 1 mole of that chlorine. All right, so similar game that we had to play with our enthalpy here. Okay, now we got to be careful. If we look at our compound formula here, it is not just Cl all by itself, but Cl2, diatomic chlorine gas. So I'm not going to be able to use this conversion factor right here. What am I going to have to do? I got to multiply it by 2. So really what I'm going to use in my math here is this 70.9054 grams of Cl2 are in 1 mole of Cl2. All right, we're going to have to take that molar mass and multiply it by 2. All right, and then we talked about how for our enthalpy, in order to use that, we're going to play a similar game. We're going to take these units of kilojoules per mole, and we're going to split it up so that the kilojoules are on top, negative 148 kilojoules per 1 mole. And this is per mole of what? This is our reaction that's occurring. All right, so now I'm going to set up my problem with my 4.5 grams of chlorine. I'm going to need to divide that by that molar mass to get rid of those units of grams. Whoops. And now from my balanced chemical equation, I'm going to use this stoichiometric ratio that tells me that 1 mole of chlorine is consumed per mole of my reaction. All right, and then my last step here would be to multiply by that enthalpy value. Oh, whoops. All right, so here's my calculation all lined up here. I first convert from grams to moles of Cl2 using that molar mass. I then can convert to moles reaction using that stoichiometric ratio from my balanced chemical equation. And then finally, I can get from moles reaction to kilojoules using that delta H, using that change in enthalpy for that reaction. What's up?
On my calculator, maybe I did it wrong.
Oh, no. I did it wrong. I see. Hold on. Yeah, it should be half that amount. Just making sure we're paying attention. Negative 9.39. Okay, and then so my units are going to work out to be what here? Kilojoules, right? The grams canceled out when I did my molar mass. Moles of chlorine canceled out from my stoichiometric ratio. And then from my delta H value, moles of reaction canceled out, leaving me with just units of energy, just units of kilojoules. And then my last step is, of course, sig figs. Our mole ratios are exact, but we do have to look at our molar masses and our enthalpy values, both measurements. In this case, I'm still limited by that initial 4.5 grams. So negative 9.4 kilojoules of energy is what? Absorbed or released by this reaction? Released. All right, so we spent a lot of time talking about calculating these enthalpy values last week. We had a few different methods for doing it. So once we have these enthalpy values, what can we do with it? Well, importantly, those enthalpy values that we calculated are in kilojoules per mole, and that's mole of reaction as written by your balanced chemical equation. So if you use a specific amount of, for example, chlorine, then you're going to have to calculate exactly how much heat is being released using your mole ratio that you get from that balanced chemical equation, right? So this is our balanced chemical equation as written is 1 mole reaction. So in this case, my 1 out front of my chlorine says that there's 1 mole of chlorine that's consumed per mole of reaction. All right, once we get to mole of reaction, we can then use that enthalpy value. Similar to how we have a molar mass, we have to convert that into something that we can use in our math. And what we're going to do is we're going to take those units and split them up. So now we have kilojoules over 1 mole. And again, that mole is a mole of reaction. And so that's how we plug it in to our calculation here, making sure that our units cancel out and that we're left with kilojoules, our final answer in energy. All right. Cool. All right, so let's just end it there. I don't want to pick up on our last topic. We got one more thing to discuss with regard to our thermodynamics chapter, and then we're done with all of our new material for this semester, all right? So we got one more lecture to go. Hang in there. Friday, we will be doing a review session in preparation for your 4th exam.